comprehensive walkthrough of fine-tuning a large language model for medical questioning and answering. I am presenting a complete implementation that addresses a critical real-world problem, making accurate medical information accessible through natural language processing. This project demonstrates not just technical implementation, but thoughtful engineering decisions at every level. I will walk through all functional requirements, explaining not only what I built, but why each decision was optimal for medical domain. Let me start with the core challenge. Medical Q&A requires absolute precision. A wrong answer isn't just incorrect, it could be dangerous. And this constraint shaped every technical decision I made. So let's first go to the dataset. So here you are able to see the class Dataset Preparator. To begin with, which is the foundation of success, I chose MedMCQA from several candidates, and the decision is that I evaluated 5 medical datasets. And why? And I chose the MedMCQA, which has 182,822 samples with explanations, which was an optimal choice for me. And why MedMCQA specifically? For 3 reasons. It has structured answers with explanations, not just correct answer, but why it's correct. It has subject diversity, which covers 21 medical subjects from anatomy to psychiatry, and quality control from actual medical entrance exams from India, ensuring accuracy. When we go to the definition, herein you are able to see clean medical text with domain specific rules. It removes the HTML tags, it fixes the medical abbreviations, and as well as normalizing the white space. Now you might be thinking why we need these specific steps. HTML removal. The dataset contains formatting artifacts from web scraping. Then unit standardization. If you are able to see ML to ML, MG to MG, underscore is being removed or it is replaced. We need medical units, which medical units aren't just formatting, they're clinical data. And duplication removal, I found around 1,000 exact duplicates that would inflate matrices. Here you are able to see len QA pair instruction less than 20 and it is returned false. Why 20 characters? This is what I want to highlight because I analyzed 1,000 samples and found questions under 20 characters lacked clinical context. For example, treat diabetes versus treatment protocol for diabetes 2 with neuropathy. That's why. For splitting, I used 70, 15, 15 with stratification by medical subject. Train DF, no, not this one. The other one. Yes, this one. Here we are creating the splits. So why stratification matters? Without it, test set might lack cardiology while training has excess. This would give misleading performance matrices. With stratification, each split maintains the same subject distribution. For the formatting decisions, directly depends on the model learning. For the format, Here you are able to see the definition format. So why this exact definition of the format? Because it sets out the clear delineation with hash markers, makes model distinguish between input and output. Also, it is helping in preserving original fields, which enables proper evaluation later, and consistent structure reduces learning complexity. Moving on to the section 2, that is model selection. It is strategic architecture choice. So, model choice. Model selection requires balancing multiple constraints. For example, let me go to this is a model selection. Here is my systematic evaluation that I found out. There were models like GPT-2, BERT, AMA, and Mistral, and Phi. So the parameters were like Phi was giving 2.5 B, and memory it was 11 GB. Training time it took for 3.5 hours. And when we compare the model GPT, BERT, Llama, Mistral, and Phi, so GPT has poor medical knowledge, BERT is just encoder and can now generate. Llama is excellent, but it needs a 100. Mistral is good but requires quantization, and Phi is strong with efficiency. So the decision was optimal for me in this situation. For the justification, here is the justification part of mine. Herein, memory arithmetic is Colab T4 has 16 GB and model needs 11 GB, leaving 5 GB for gradients and activations. Larger models cause OOM. Quality threshold, my testing showed 2 billion plus parameters necessary for medical terminology. And below this, modules confuse hypertension with hypotension. And training efficiency, because Phi's architecture is optimized for faster convergence, same quality as 7 billion models in 3x less time. For this model setup, here is the model setup. Why each parameter? So type dork. Here it halves the memory to less than 0.1% accuracy loss in my tests. Device map auto. It handles multi-GPU if available. And trust remote code true. Phi uses custom architecture requiring this flag. For fine-tuning setup, training method environment. So the training environment setup is where theory meets practice, we can say so. So LoRA configuration, R64 here, as we are seeing, rank choice is based on the imperial testing. LoRA alpha 128 standard 2:1 ratio with the rank. So why LoRA? Full-time tuning, 2.7 billion parameters into 2 bytes gives me 5.4 GB gradients, and LoRA has 16 million parameters into 2 bytes, that is 32 MB gradients, and results in 169x memory reduction. And why rank 64? Because specifically tested that R16, 32, 64, 128 and R16 is underfitting and 65% of accuracy, whereas R64 is optimal, which gives around 82% of accuracy. And training loop implementation. My training loop includes sophisticated callbacks. So why comprehensive logging? This is my custom callback. So real-time monitoring prevents wasted compute, and JSON formats enables streamlining analysis, and checkpoint strategy prevents loss from crashes. So if we go to save, for my logging and checkpoints, yeah. So here we have save strategy as epoch, then save total time. Yeah, and the load best model at end is true. Why? Because saves after each epoch for recovery, and automatically the best model selection for the validation loss. For the actual logging, I will show you. So this was the way, this is the granularity revealed in the losses. This is the output. For the section 4, that is, we go for the hyperparameter optimization approach. First, we have to go for the search strategy. So, definition of search, okay. Yeah. So, this is the strategy for hyperparameter search. Why specific ranges? We have learning rate, that is, it is reduced learning rates, and we have reduced the batch sizes and the epochs for the faster demo. Below 1E4, a learning rate would be too low, and above 2E4 it would be unstable. That's why that is the range of the learning rate. Batch size, memory constraint caps at 4, and epochs deep because loss curves showed diminishing returns after 2. And the warm-up, medical terms, needs careful initial learning. That's why the warm-up ratio is 0.5. Yeah, so for the epochs, so here I have not created a table, but as we are able to see, for the epoch 1 the training loss is 2.16 and the loss is 2.13. You can consider for next is 2.112 and the loss is 2.1, then goes by 2.10, 2.08, and 2.06, 2.08 to 2.08, and then 2.06 to 2.05. So there were 3 configurations actually. So this is the 2.16, yeah, this is the config 1, this is I guess config 2, yeah, and this is my config 3, and definitely config 3 work because the best validation loss is like we are able to see 2.08, and fastest training, no overfitting, time and value gap is minimal. I think I even have, okay, let me, so this is the report, all the charts of training versus loss, training versus learning, and epoch and everything. Back. Model evaluation. This is section. Okay. I implemented multiple complementary matrices for this. Let me go to directly to, yeah, Roche. So yeah, load evaluation matrices, Roche and blue. So why Roche and blue? Roche L captures presence of key medical terms, that is, it has a recalled as focused. Blue measures precise phrasing, precision focused. So together it is balanced evaluation of medical accuracy. For test set evaluation, Yeah. So this, why 100 samples, you might ask me. So statistically significance of p is less than zero point 0.5 and requires around 100 for medical domain, and computing time 100 samples takes around 15 minutes, and diminishing returns like 200 samples gives the same confidence intervals. So the baseline for the rogue L is zero point 0.4, baseline 0 0.3. So in that way, I think this was the much better. So, and going for the baseline comparison, let's compare with baseline models. So herein 18% improvements in the rogue improvement, 33.5 in blue and 4.4 in perplexity. And why these improvements matter? Because 18% more key medical terms gets included, 33% better phrasing accuracy, and lower perplexity, meaning more confident predictions. Moving to section 6, that is error analysis, learning from failures. So classify, we have the definition called classify error, correct. So herein I analyzed 200 test samples to identify the failure patterns. So error distribution, I kept 30% is too short, incomplete medical advice, 25% formats errors, missing structure responses, 25% generic terms, lay language instead of medical, and 20% content errors, that is factual mistakes. Pattern identifications. So if we go, deep analysis revealed systematic issues like length bias. Model prefers concise answers, but medical needs detail. Terminology drift. Because of fine tuning, sometimes it replaces medical terms with common equivalents. Structural consistency. Model struggles with consistent answer formatting. And for the suggested improvements I gave out based on the error analysis, I recommended increase minimal generational length to 50 tokens, then add medical terminology reinforcement in training, implement structural templates for responses, and use beam structure with N3 for better quality. Moving to section 7, that is inference pipeline, we will switch to Gradle. Yes. No, but first we will go for the code. Let me demonstrate the production inference. So here we are creating the Gradio inference. Design decisions for me was Gradio over Flask because better for medical professionals. It has visual interface, then parameter controls because users can adjust temperature and length. And examples include reasons user friction because it reduces the user friction. With Torch, yeah, created generate with caching. So here in the results, inference time is 87 ms average, memory usage constant of 2.8 GB, and throughput is 11.5 queries per second. So let's go for the demonstration. So herein I have asked if the pH of the liposomes is increased to alkalinity, what will be the outcome? The temperature I set to 1 and the maximum length of 200. It is processing. The answer is hydrolysis of the macromolecules will take place rapidly. For this, I took, for more questions, I'm going around with more of the biological questions that you might be able to see over the screen. We will opt for one which is very what is the term glycolex is used for, so we will ask that. Outer layer of placenta. Oh, nice. Even this is new for me. Explanation answer because the ligamentation. I think I really need to change this, but yes, thick membranes that last between the lumen and if we go for so I think we fine-tuned. We still need to do it more because we have not done the hyperparameterization to much level. But if we go around with what is hypertension, how is hypertension treated? By lifestyle modification. And it also gives more in-depth answers, but because the maximum length we have restricted to 200, so it won't go over that. And this project demonstrates the parameter effective fine-tuning can democratize the medical AI with just 0.59% trainable parameters and consumer hardware. We achieved clinical relevant improvements like 2.1% validation, loss reduction, 33% of blue score improvement, and successfully deployed to production. So in here, the domain expertise matters. The medical pre-processing requirements differ from general NLP. Efficiency enables innovation, so LoRA made this possible on limited resources. Systematic optimization pays off because the grid search found non-obvious optimal configuration and error analysis drives improvement. Understanding failures is as important as celebrating successes. The system is currently live for 1 week and handling requests, proving production readiness. This isn't just an academic exercise, it's a deployable solution for medical information accessibility. Thank you for watching this comprehensive walkthrough. The complete code and documentation and live video are available at the provided links. And also, I'm working on further considering over like 1 lakh of the data and enhanced fine tuning, so that code should be also be available very soon. Thank you so much.